This is a video for AQA Further Pure Mathematics, Numerical Methods, Section 2.1, which considers Euler's step-by-step method for solving differential equations. We've seen previously how many differential equations can be used to model real-world situations, and we can find those solutions by analytical methods. This you may have studied when you've looked at different equations first and second order. But there are many situations where we cannot actually solve the equations analytically, and so rather than doing that, we need to have some way of approximating the solutions. Consider, for example, this particular problem where we know that a curve passes through a point 1, 1. So we know that at some initial values we've got x0 and y0, and that we have an equation which tells us about the derivative dy by dx. In other words, we know the gradient at that point. But you can see that this is a non-linear equation, so we can't solve it by the methods that you have met so far. But we can by using the idea that we know a point and we know the gradient at that point, then calculate approximations to what happens after that. And one of the simplest ways of doing that is to assume that the lines are straight lines, and this is what's referred to as Euler's step-by-step method. So this diagram then illustrates what we know at the moment. We've got our initial point 1, 1, and we know that its gradient dy by dx is given by x plus square root of y. And so that's illustrated by the dotted blue line. So if we say that that blue line there is going to be an approximation to the curve, then what we want to do is to calculate the values at this point here. That of course will depend on the interval size that we're choosing. So let's choose here a value of x to increase by 0.1, so that the new x value is going to be 1.1, and what we want to do is to calculate the new y value. Let's call it y1. The differential equation that we've got dy by dx is equal to x plus root y gives us a way of calculating the gradient at our initial point 1, 1. So the gradient at 1, 1 will be equal to the x value, which is 1, plus the square root of the y value, which is also 1. In other words, the gradient is equal to 2. But we can also calculate the gradient at that point by using this right-angled triangle down here, where we need the increase in the y value, that will just be y1 minus 1, and dividing by the increase in the x value, which we've chosen to be 0.1. So we can say that therefore the gradient which we've calculated by the differential equation dy by dx is 2 must be equal to y1 minus 1, the increase in the y value, divided by 0.1. And therefore we get that y1 is equal to 1 plus 2 times 0.1, which is 1.2. So we've calculated the new x and y values for this point here, assuming that it's a straight line section, and that will be an approximation. So the 1.1 and 1.2 will be an approximation to the exact value which is on the curve. Well, the next step is then to repeat that process and say, well, what happens if we move along a further distance of 0.1 and we then calculate the gradient based on that point that we found to work out this point here, which we can call x2 and y2. On the next slide, I've got that presented for you. So here we have the x value, which is obviously going to be 1.2, and we need to calculate the y value, y2. But it's the same process. We can calculate the gradient at our assumed point 1.1, 1.2 by using the differential equation. So substituting 1.1 and 1.2 into here gives us a gradient at that point of 2.195. But that gradient is equal to the increase in the y value, which is y2 minus 1.2, which is the value of y1 that we'd found, divided by the x value 0.1. And that gives us an approximation for y2 of 1.4195 to 4 decimal places. Euler's method then uses the idea that we can approximate a curve by a series of straight lines where the straight line has a gradient equal to the derivative at the start of the interval. The value of the gradient can be found from the derivative, which will be given by some function of x and y. Let's call it f of xy. So we can substitute our first point, our known point y0 and x0, into that function to give us a value of the gradient. But that gradient can also be found by using the fact that we're approximating by a straight line, so it's y1 minus y0 over h. So that gives us this formula for y1. The process can then be repeated over and over again to get y2, y3, etc. In general, then we get this formula here that yr plus 1 is equal to yr plus h times f of xr plus yr, where h is the interval size and the derivative is given by the function f, and that will be in general a function of x and y. Now obviously this is going to increase in accuracy if we reduce the size of h. But reducing the size of h is then going to increase the number of calculations that are required to reach any particular value of x that we want to. Because of that, then doing this on paper becomes quite tedious. And so in exam questions you'll probably only be asked to find y1 or perhaps y2 for a particular situation. However, if this was to be done in practice, it can be done by computerizing the formula, which is quite straightforward, or to do this calculation on a spreadsheet. Well, that concludes this video on Euler's step-by-step method. And in subsequent videos we'll be looking at how this can be improved so that the accuracy is better, so that the errors involved in the method are reduced. So we'll be looking at the midpoint formula and then what is called the improved Euler's method in a subsequent video.